Thank you for being here for the third lecture. So last time we saw very briefly, at the very end of the last lecture, we saw very briefly some more formal stuff. We saw what the manifold is. It is basically obtained by taking various open sets with sets of coordinates. So they can be thought of as open sets in Rn. And we then use so-called transition functions to glue these open sets together. What this means is that we declare that a point whose coordinate is xm alpha in the open set alpha is identified with the point on the other open set beta if it is the 2 points are related by this transition function. Okay, this is a very informal and maybe not very informative discussion of what a manifold is, but I hope it gives you the idea. You just glue, according to some laws, pieces of R to the n, and the reason this is a good idea is that we know anyway how to do geometry, how to define vector fields and so on in any coordinate system. So changing from one coordinate system to another in any way we like is something we know how to do. We then saw what the bundle is, also very briefly, but basically it is a similar idea where you now the objects that glue objects that are more special. They are still open sets, but they are made of Cartesian products of an open set of the type that we glue to obtain a manifold. Cartesian product with a certain other space called the fiber. And then the transition functions are that glue this U hat are made of 2 components, one that glues the U's in the way we saw earlier, and another which glues the fibers F. Now these have a special shape, a special form, because they, for example, F could be a vector space. In such case, the natural way to take a transition function is as a matrix T alpha beta, say, which we also call a transition function, but for bundles, acting as a matrix does on F beta, which is an element in the fiber. The examples we saw are the tangent bundle and the cotangent bundle, where now the fiber in both these cases is again a copy of Rn, and what it represents, for example, in the case of the tangent bundle, is the space of all vectors. Given a point, you have that the fiber is the space of all vectors, vector fields evaluated at that point. So these are this is now the fiber. Actually, this is just one example, and there are many other bundles that are naturally associated to a manifold. You'll notice that this is still in a natural way associated to a manifold. You can consider this is the bundle of vector fields, but there could be there is the bundle of the cotangent is the bundle of one forms, but you could keep going and consider the bundles of K forms, for example, and so on. Now we are going to see that sometimes these transition functions can be quote-unquote reduced. What do I mean? This T alpha beta in general on a general manifold, like this, are usually in GLN, GLD. But sometimes we can actually show on a certain manifolds, we can actually show that they are actually valued in a smaller space. And that's called the reduction on the bundle. So on a smaller group, sorry, this is the group of all invertible matrices, but we could very well encounter a situation where they are valued in a smaller space. How could that happen? Well, for example, already if you have a metric that makes sense globally, then it turns out that you can take this the transition functions in a smaller group. So basically this is because remember that from the metric transforms under changes of basis and sorry, changes of coordinates in this fashion. But well, if the J tilde is now well, J is, remember, this is the general transformation law. But now for us, from an open set to another, what they're doing is we are given how the G beta is obtained from the G alpha. But now consider, for example, an orthonormal basis. A Filbine. The metric in orthonormal basis if there is no time, for example, in the Riemannian case without the time, not the Lorentzian case. It's like the identity. What this means is that the inner products just behave like delta AB. But of course, this was the definition. But now think about it. This means that there is a basis on each open set where the metric reads like delta AB. Careful, this doesn't, I'm not saying, of course, that there is a coordinate system where the metric looks like delta AB, because that would mean that the metric is flat. I'm just saying that there's a basis where this is true. But if you translate so this condition, this transformation law, this is going to say that the J tilde written in this basis we'll say schematically that the identity, because now the metric is the identity in this basis, will be sent to J tilde times the identity times J tilde transpose. So, however, also in the new open set, you can take a new vielbein. So this will be you have a vielbein in open set alpha, but there will be another vielbein in the coordinate set beta and so on. And you can, if you take this choice, well, this will also be, this will be the identity on alpha, but you will have also the identity on beta. It feels silly to have alpha, this alpha index here, just to emphasize that you can write this as being the identity in each open set. I can be more explicit if you like. So basically, you this J tilde. So here we can write this as J alpha beta to emphasize that it goes from the open set alpha to the open set beta. Well, this J tilde Mn will be, we can translate it in, we can write it in terms of a new matrix. Let's call it lambda or O. Let's change the name here. Let me call it O. O A B E B N. If you work out the relation between this J tilde and the relation defined in G in terms of the vielbein, you will get to this transformation law. But now, what does this tell us about O? Well, O transpose gives the identity. So O is, as the name suggests, in ON. So the OD. So the transition functions started their life as valued in GL, but now we discover that they can be written in terms of some matrices that actually live in O instead of GL. So this is already our first reduction of the structural group. The structural group is the group in which the transition function are taking values. And in other words, we have discovered that they can actually be reduced to OD. So this one says that the structure group has been reduced. Now, why were we able to do this? Thanks to a metric on the space. Now, it turns out that basically on all manifolds, you can do that. There is a metric called almost on any manifold. There's a condition called para compactness, but that is something that in physics goes without saying. So the transition functions can, for us, we can always think of them as being an OD. But if we want to reduce further to even smaller subgroup, then we need to assume the existence of more complicated, of more non-trivial objects. Some examples. if you have a vector field that is never zero, nowhere. Well, then this O alpha beta, here I suppressed the alpha beta indices, but well, perhaps it was not a good idea to suppress them. So let me see. Is the formula more complicated? But also clearer. Well, then it turns out that this O alpha beta reduces the further. Why? Well, because again, express this vector field in the field-bind basis. In fact, you could even imagine saying that this is the choosing your field-bind in such a way that this is your E1. So you can look for a field-bind that starts like that. Of course, a vector field that is over zero might have a function in front of E1, but for simplicity, let's just say that it is E1. So we can rescale things so that this is 1. After all, it is nowhere zero. Well, then it turns out that the transition functions, schematically, we have to, if I set this vector field equal to E1 on every U alpha, which I can do again, but I can move I can choose the vector field in the field bind in this way. I just start with this. I give my vector field and then I look for the other ones in such a way that they are orthogonal to the first one. Then the condition that the transition functions needs to satisfy is this. But again, E1 is the first vector, so really it means that it is in the field bind basis, it just looks like this. Dot, 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 0. It's the first vector of the basis. So O now satisfies this condition. So in fact, let's say no D minus 1. So this is a further reduction. Now, such a vector field that is nowhere zero is not easy to find in general. It is famously impossible to consider such a vector field on a sphere. There is no smooth choice of a vector field on a sphere that is nowhere zero. This is the statement that a two-sphere, for example, cannot be combed. It is possible in odd-dimensional spheres, but for example, not on a two-dimensional sphere. If you try to write such a vector field, you will always find two singularities, two points where the vector field is not smooth, or where it is zero. But so it is, this case is more meaningful than the case with that we considered earlier, where the existence of a metric does not impose much of a condition. And it is more representative of what happens in general. In order to reduce the structure group to something smaller than OD, you usually need to assume something topologically non-trivial. So there are many other examples like this, but so in fact I can say that this is only possible when the so-called Euler characteristic is 0, and this is the alternating sum of the homology groups. Since we talked about the homology groups, this is an application. I was saying there are many examples like this that are relevant in mathematics, but for us, we will not be really interested in the existence of a globally defined vector per se, but we are interested in the existence of an over-vanishing spinor. Now, this story of going to the Filbine basis is even more relevant because we saw that spinors are defined naturally to the Filbine. The analog of this story here is as follows. Basically, you set again eta equal to something definite. Let's call it eta 0 on every u alpha. This is what we are doing also in the previous cases. And now, what you want to write is exactly the analog of this. So there will be, you need to talk about the action of this O on eta, but remember that so this action is not trivial. I mean, we wrote it last time when we talked about spinors by saying that in terms of gamma matrices, so remember that if you have an element of OD, and we write it as exponential of some antisymmetric matrix, well then really let's call this as rho S of O. What do I mean by this notation? Well, I'm now emphasizing that it is acting in a certain representation, in the spinorial representation. And this was defined last time with this formula, where omega slash is itself 1/2 omega mu gamma mu. So now, well, in this case, in the previous case, it was pretty easy to see what this condition amounted to. Well, because you have an orthogonal matrix that leaves invariant one vector, it only rotates the remaining vectors. So it's as if it were orthogonal matrix in the remaining directions. But now for spinors, it is, I think, less intuitive what this result is. What this will be clear that O is reduced. But reduced to what? We need to figure out. So the answer, so what we can say is that by definition, O will be in the stabilizer of this eta 0, the special spinor that we have taken our eta to be like. But this is just the stabilizer is just defined as the O's such that this is true, whose action on eta 0 gives eta 0 again. So I haven't really said anything. What is this stabilizer? Well, let's see. We can actually do the computation in several cases. But the answer actually depends on which dimension we are and on some other details, such as what if I take eta to be completely generic, or if it is if it obeys some reality conditions, for example. But let's take, for example, d equal 4. And let's take again Euclidean. So the metric doesn't have time. So it is, in other words, a Riemannian metric. What we have seen is that we have seen a basis but let me remind you what the basis was. These are the 4 vectors in this basis. And what I haven't told you is that given that this is a low dimension, any spinor that is chiral, let's say of chirality plus, can be brought to the form plus plus via this spinorial action. So you take a rotation in space, you associate this spinorial representation of the rotation in space, you act on this plus plus, on your any chiral spinor you have, and of chirality plus, and you will be able to bring it to this form. Actually, in this case, so you can do the exercise, it is not that complicated. Because after all, in 4 dimensions, there are only 2, so the space of spinors in of chirality plus is only 2-dimensional. It consists of the generators are just plus plus and minus minus, because the chirality is just a product of the signs defining this basis. So here. dt plus minus minus plus. So in this case, all you need to show is that you can set to 0 the coefficient of this minus minus. It turns out that also in dimension 6, where there are the space of Karl spinors is actually 4 dimensional. Also in that case, you can bring the spinor to one particular form, such as plus plus plus. In higher dimensions, this is not true. Not any spinor can be brought to this form. Actually, this is a special property. Any spinor that can be brought to this form is called pure. What does it mean? Well, let me write it like this. It means that formally we say that the annihilator of let's call this theta 0 has dimension d over 2. Why? Why is this true for this theta 0, 0? So this is the general definition. The spinor is called pure whenever the annihilator has dimension d over 2. In this case, d over 2 is just 2 because we are in d equal 4. And how do I know that the annihilator has dimension 2? Well, because the two annihilators, the two generators of the annihilator are this gamma I. So in this case, this is the span of these two. And why is this true? Well, you may remember that in this creator-annihilator basis, first of all, we were thinking of plus as 1, 0. And so the gamma I bar was made of creators. And this is already, plus is already the highest possibility. So these two are creators. Gamma 1 bar is consists of a creator. I remind you, it is not that far ago, that long ago. There's this formula here. So gamma 1 is the creator in the first entry. So these are the gamma 1, and this B would be the annihilator. So the gamma 1 bar would be B dagger creator. Tensor the identity, so it creates on the it takes a minus into a plus on the first entry, and the gamma 2 bar does the same, except it also has this sigma 3. Okay, given that we didn't have it, let's write it now. This is gamma 1 bar and gamma 2 bar sigma 3 tensor B dagger. So this is the reason that that these two are annihilators. Now let's try to compute this this annihilator. How do I do it? Well, it's not that hard. So remember here we are exponentiating this instead of instead of looking at the group of this O's in the stabilizer, let me look at the infinitesimal action. So and if I want the finite version here, this exponential of the 1/2 omega slash to leave at a naught, to map at a naught into itself at the infinitesimal level, it has to give 0. So that when you exponentiate 0, you get 1. You get, so when you exponentiate this relation, you will get this. If infinitesimally you leave something invariant at the finite level, so if the infinitesimal expand this exponential, if you expand it at first order, well, the first order will give 0 on eta 0, and then also all the other orders will do so. So the only part of this exponential that will remain will be the 1, the stupid part, and that will give eta 0 at the end. So the condition that is easier to impose is this. And now let me write omega in a complex basis. So instead of writing it as in real coordinates like this, I can write it in complex coordinates. It would be like this, plus just the complex conjugate of this. So there will be a case with all with holomorphic indices, a case with anti-holomorphic indices. Put bars here, and then a case with mixed indices. I don't write the I bar j part because it can be rewritten using anti-symmetry in terms of this one, which is also the reason I didn't put 1/2 here. Okay, so we can now, why do I do this? Because I know the gamma matrices are easier in this basis when written in complex coordinates. And well, you see immediately that the part with omega, so it is true that the creators automatically disappear, but the part involving the annihilators doesn't automatically disappear. So in particular, anything, so this omega 1, 2 would not be 0. It is here, sorry, slightly wrong. this peculiarity of this complex indices is that the gamma 1 bar, for example, well, you raise the index with the metric, but it turns out that the non-zero component of the metric is G1 bar 1. If you look at how we wrote the metric in these coordinates last time. And this is actually a 2. But more importantly, the now index has been transformed from a barred one to a non-barred one. So when you raise and lower an index, you gain or lose a bar. Now you see that if gamma 1 lower bar gives 0, gamma 1 upper bar doesn't. And in particular, this one would just give minus minus proportion to minus minus. Now, you might think that as a consequence, anything with a bar needs to go away. For example, this one, well, here you will be right. Sorry, here you see the 2 bar, yes, you will be right in thinking that it gives a minus, but the gamma 1 now, with the upper one, is a creator, and so again gives 0. So this is this goes to 0. And you might think that this is it. However, if you consider one bar, or 2 bar, this is no longer true because gamma 1 bar is not quite equal to gamma 1 bar, because if you consider gamma m, gamma n, this is the 1/2 the anti-commutator plus 1/2 the commutator. The anti-commutator just gives Gmn. The commutator gives us what we called gamma mn. So conversely, gamma mn is gamma n minus Gmn. So here we have a gamma 1 bar, and this does kill plus plus because there is one creator here, gamma 1. However, there is also this extra term, minus G11 bar. And this does not give 0. Okay, I'm doing this a bit schematically. Hopefully, I'm giving you the idea of what's going on. But let me now tell you the final result. So the final result is that you need to set to 0. So basically, what you can say is that I called it theta 0, but let me call it theta 0 plus. After all, we have to remember that it is of positive chirality. Okay, here's our example. So to summarize our discussion here, we see that this is automatically 0, but these guys here with the barred indices don't give which are up. don't give automatically 0. And this story that I was trying to tell you here can be summarized as saying that gamma ij bar on this guy doesn't quite give 0 automatically, but it gives, it turns out that the right coefficient is this. Here we were getting -2 instead of -1/2 because I was considering upper indices instead of lower ones. But so you see the coefficients, so this need to be 0. And then we have something to impose on the omega I j bar. And the final result is that the stabilizer, the Lie algebra, let's say I write here S with lowercase to tell us that this is now the space of omegas, Liddell omegas. Well, this space is the linear span of, well, in this case, we can just put a 1 here. So we can take, for example, gamma 1 bar minus gamma 2 bar and gamma 1 bar. These are 2 objects that belong here. So this is complex, and this is real. It's purely imaginary, so let me write it like this. So now it is real. So a total of 3 generators in this stabilizer. What is this, the Lie algebra spanned by these guys? We can find out by taking commutators, but I'll just tell you that it is isomorphic to SU2, which is indeed 3-dimensional. You can think of it this way. The condition that it shouldn't have any parts like this, you see we set to 0 the coefficients that are that have 2 bars. And by reality, then we should also set to 0 those without bars. And this conjugation takes a bar to a no bar. That has something to do with the fact that this infinitesimal rotation omega doesn't mix a complex coordinate with a non-complex coordinate. It is perhaps clearer if I write it as omega I j bar is 0. So you see that this infinitesimal rotation doesn't mix a complex index with a non-complex index. And this already tells us that we expect this matrix to be in U2. Now, if this were the only condition, we would have that the generators are gamma ij bar, and this would span the algebra U2. But the fact that I subtract this extra term makes it so that now instead of being U2, it is SU2. We have basically subtracted the trace. Hence, the reduction to SU2. You can view it, remember this, so this subtraction on the trace comes about basically because we do have a condition on the omega ij bar as well. Okay, good. So this is what we have found in 4 dimensions in general. You consider a spin of this type, which will again be pure, in the sense that they will be annihilated by all the gamma I bar. Then again, the stabilizer will be SU d over 2 by generalizing this computation we have just made. So it is clear that we have not, this language is a bit clumsy, so perhaps we can do a little better. So we can do better if we introduce some tensors, some extra tensors. Instead of saying characterizing the stabilizer in this fashion, we can say that it is it has this form. Where omega is now tensor, which is like the volume form, in the sense that it is its components are given by the Levi-Civita tensor, but only for the holomorphic indices. And these are the only non-zero components. In other words, omega will be an exterior product of all the holomorphic, of all the complex coordinates. And this is this condition here. It captures this condition that we had here, that only that the omegas 1, 2 in this case, without bars lower, were 0. Now, in general, but we saw that there's another condition, and this can be written as follows, where now J is defined as this. Sorry, to put a minus sign. Now, I have been doing this computation as in a flat space, basically. So this is in general wrong. And in particular, what doesn't work in general is that we have coordinates dz where we can write this the omega in this fashion. What we can really do is to find Filbine which is holomorphic. I call it HI. And it's a complex conjugate. And now these give exactly the metric, the flat metric, but in holomorphic coordinates. Strictly speaking, perhaps it would be a good idea to stress that this I is a flat index now, as we were doing in real coordinates, but that becomes a bit heavy to have a fourth type of index, so I have kept here the index I, but it should be thought of as a flat index. And now a better way to write this in general is this. And in real indices, we can more correctly replace this with flat indices and so on. Now, we are going to explore, so this is the most important structure for us. We are going to explore what it means to what this type of structure entails for us. So what we have discovered is that the Carrel spinor, which is never zero, nowhere zero, gives a reduction to SU d over 2. In particular, when it is pure. This condition is automatic in d equal 4 and 6. in particular for us, 4 and really 6 will be important. And now we're going to explore various conditions on this complex structure, and this will take us to on this reduction, and this will take us to the geometries that are important in string theory. But now let's take a break. Fantastic. So we can now study a bit more this reduction. In fact, people call this SU d/2 structure. The data of this reduction of the structure group. So something happened. Something bad. I don't know what I touched. Very good. So we can now study this reduction to SU d/2 in more detail. So people just call this an SU structure. And what we just saw is that it is either the choice of rather than an equality, the choice of a pure spinor, but also it can be characterized with these objects here, with this J and this omega. These are forms. There's a 2 form, because there's 2 indices after all. And omega is d/2. J is real, d/2 form. Complex. Now, so far we know nothing differential about these 2 objects, but let me point out a couple of things that are algebraic, and then some other algebraic properties of these objects, and then I'll move on to study of their differential properties. So first of all, I introduced also a holomorphic Hilbert, so the space of forms that have P holomorphic Hilbert and Q anti-holomorphic ones is well, the space of forms is denoted usually as lambda T star. So the bundle of forms, let's say, is denoted with lambda T star. The lambda is to remind us of this wedge exterior product symbol. If we more specifically, if we want to talk about the K forms, we write a lambda K. But if we have forms of this kind, we call them PQ forms, and we write lambda PQ. Now, it immediately follows that omega is d over 2 comma 0 form, and j, well, its non-zero indices are, you see, one barred and the other unbarred. So it is a 1 comma 1 form. Now, I can already tell you, as promised, a couple of properties. So one is the following. Why do I say this? Well, omega is already the wedge product of all the holomorphic elements of the field bind. So there are only d over 2 of these, and you cannot take a wedge with the further one and not get 0. So this would be, in other words, a d over 2 plus 1 comma 0 form, but there is no such a form. So this is 0 automatically. And another thing you can notice is that you can consider the wedge product with its complex conjugate, and you will get a volume form, something proportional to a volume form. So the another way to get a volume form is actually to get J exterior product with itself. It turns out you can check this, that if you, for example, we wrote here omega in this fashion and J in this other fashion, but I can also give you, so once I wrote it like this, I can also this is exactly the same. This is basically the same relation. I don't know where this minus came from. I think this is a plus. So if you take a exterior product of this with itself, for example, this is H1, H1 bar, H plus H2, H2 bar, and so on. If you take the wedge product with itself, it will keep being non-zero until you take the wedge product with itself d over 2 times. And let me define this to be j to the power d over 2. Both of these are proportional to the volume form. That we saw last time. After all, J, remember, is a 2 form. It is a 1 comma 1 form, but in particular 2 form. So it's if you take d over 2 wedge with its d over 2 times a wedge with itself, you get a d form, which is the correct degree for volume form. And omega is a d over 2 form, so the omega bar also, so the wedge product also gives you a form of top degree. Important case. D equals 6, then the I can give you, I could give them in general, but let me give them for this case. Here I just wrote proportional. This symbol is proportionality, but here for d equals 6, I'm giving you the actual numbers. This is so this condition and this other condition are an alternative characterization of omega j that define NSU structure. Actually, from now on, I will mostly have in mind that d equals 6 case because of physics, but you can bear in mind that any of the things I will say easily generalized to any other dimension. So still with d equals 6, I can also, it is also sometimes useful to express these forms, which we extracted from the annihilator of eta in terms of eta itself. It is possible to do this. And let me write the formula, and perhaps I can then explain it a little better. So for omega, and what do I mean? So if eta plus is of this form, eta minus will be of, in a sense, maximally distant from it, but it is also we can also define it as the star of eta plus. And there's a similar formula for J. And sometimes these are called, when written in this form, these are called spinor bilinears. Why bilinears? Because they are quadratic, and maybe they could be called quadratic because the etas appear twice. You can check that if you put plus 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 here, minus 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 here, the only non-zero possibilities here are exactly when the gammas are taken with two lower indices that are non-barred, because after all, the ones that are barred automatically annihilate eta plus. So this is the idea behind this definition. Nothing really fancy. And similarly, you can check that the only way that you get non-zero in the second formula is if you take gamma along these directions, I, j bar, with the delta I, j bar. Now, on to differential properties. Sometimes when I want to write something fancy, I'm too small. So we start from the most important differential property I want to highlight is regards the complex field bind. Remember that in terms of this, omega is written in this fashion as a wedge of all of them. There are d over 2, so in d equals 6, there are 3 of these h's of this holomorphic field binder, and but now I want to start with that by thinking about these. So I already mentioned this, but in general, not obvious that there exist complex coordinates such that the HI are proportional to the DZ proportional to the DZI. Nothing guarantees this. So why? Well, this is related to the fact that these are field binders. So when we work with the field bind, we are kind of pretending we work on that local tangent space to a manifold, and we are kind of pretending that everything is flat. We are working locally, but this is more sophisticated notion. So remember that the field bind, the one forms that span the field bind. So these were one forms with a special property. That this happens, and you see that they kind of trivialize the metric, but really they are something like this. With real coordinates, no problem. But who says that there is a choice of complex coordinates such that the HI are only the span of these complex coordinates and not the DZ bar I? This is not guaranteed. So if they exist, these define a complex structure. You can also turn the thing on its head and say that the complex structure is given by the choice of the complex coordinates. What is non-trivial then is that these complex coordinates have anything to do with with your original omega. This omega needs to be the holomorphic volume form with respect to some complex coordinates. Now, even if you throw away your original omega, and you say, oh, I go to a open set and I'll choose some complex coordinate any way I like. What will not be trivial then is that if you do this in every open set, that it will not be trivial that the transition functions will be holomorphic. So far we were looking at smooth manifolds. We were using the transition functions as being smooth functions from the xm alpha on open set u alpha to the xn beta on the open set beta u beta, and we only impose that the transition functions be smooth. but from a function being smooth to a function being holomorphic, there's a big difference. So if you want, this is the big reason that it may be difficult to define a complex structure on a manifold. Even if you say you don't, so there is a difficulty if I start from a spinor, first of all, then you will have this step here where you want to find the Zi so that dhi are a linear combination of the dzi only and not the dzi bar. But even if you try to reverse the thing and say, oh, I'll start with the zi and then look for an eta and an omega that relates to those dzi, well, it will not be trivial to globally pick this complex structure. So there is in a way a local abstraction if you have already a spinor in mind, but then also global abstraction even if you don't have a particular spinor in mind. This discussion maybe is a bit subtle, but I hope it will become a little clearer later. So, well, let's see. I will now give a couple of characterizations, couple of tricks, because this might look a little abstract as a condition. So, one way is to impose that so if the hi are proportional to the dzi and you take its exterior, the exterior differential of a dhi, then you see there may be functions in front, but the derivatives and the derivatives of those functions are not imposing anything on them. They might contain dzi or dzi bar, but the original dzi, so let's say if you write this more explicitly as some hi j dz, for example, well, you will get the derivatives of this hij, but this dzi will not be destroyed. So what follows from this is that the dhi should always be of the type something, let me call it psi, wedge hj. So in other words, it will never be, so the exterior differential of hi will always be something wedge some hi's. This would not be true if, for example, let's say that I encountered a situation where dh1 is h2 bar wedge h3 bar. Well, then this will violate this condition.
So here your hij is just depend on z and not z bar?
Eta.
Hij.
No, yeah, so basically I'm trying to I'm saying if h, this h here, you mean?
Yeah, the coefficients, the hij coefficients.
The coefficients can depend on anything they like, but the message is if you take d of this, you will get dhij wedge dzj, but the dzj are proportional to dhi again. They are h minus 1 times hi. So basically you will get something like dh h minus 1, sorry, schematically, if you consider h as a matrix, okay? You will get something like dh h minus 1 h again. So you will always need to have at least one h. You cannot have a situation where they're all bars. basically because you will not destroy this guy. You will have the derivatives of these guys, yes, but this will remain here. So then re-expressing the DZJ in terms of the HI, what I wrote follows. Is that clear?
Yes, thanks.
Thank you.
But in the exterior derivative, I could still have a dz bar I bar, for example.
Yes,
Okay,
but
okay.
in the exterior derivative, yes, of this
Okay.
guy,
Yeah.
No
Okay.
problem, yeah. So for example, you could have H1, H2 bar, and this is okay for this condition. So this guy can contain anything it likes.
Okay, okay. Thanks.
But so this is not that useful, I have to say, but what is useful is that since omega itself is the wedge of all the H's, you can now work out what happens to D of omega. And what happens, if you believe me, is that it will not have any part with where there are two. Sorry, this is harder to write than to say. I mean, say we take D equal 6 again, so omega is a 3 form, and in fact a 3-0 form. But because of this property here, D of it, the D can generate at most 1 H bar, never 2. So because of this, the omega, so in this case it will be 1, 2, is 0. And yet another way to say it is that the omega is always one form, any one form. It could be, well, could be any one form, but really here only the part with that is of type 0, 1 counts, because the part 1, 0 vanishes. But anyway, the omega can only be of this form. So this is a characterization of the existence of a complex structure. I have to confess, however, that my discussion has become a little less general than it could be when I introduced omega. In fact, for the more general, I'll write this organized fashion. A complex structure makes sense even without omega. So what could happen basically is that the holomorphic vielbein are defined. So the discussion up to here, you know, this part here doesn't make any sense, any reference to omega. So you could go on with the HI without ever mentioning omega, and forgetting that we are coming originally from a spinor. And as a mathematician, this definition here would make perfect sense. The moment you start using omega, you are restricting your geometry a bit. omega belongs to, as we saw, to this bundle. It is a 3-0 form for d equals 6. I'm tired of writing d over 2 every time, so let me take d equals 6. It is a 3-0 form in this case. And it turns out that it has so there is only one up to complex rescaling. So there is only one such form at every point. So this is a bundle of which is called the line bundle, whose fiber is C star. This is the very last thing I mentioned at the end of the previous lecture. What is peculiar about this, what is particular about these bundles is that, well, you can define, in this case, you can say that these forms that belong to it really make sense globally only if things that make sense globally on a bundle need the bundle on a line bundle, need the line bundle to be trivial. So basically what I'm saying is that this statement that I'm making here is even more general for, but in particular it is true here. So this condition can also be related to something that I haven't introduced for lack of time, but basically it is the same. So what I can tell you is what it means for a bundle to be trivial, namely transition functions are the identity. Notice that no one is saying that the tangent bundle has transition functions that are the identity. No, what we saw was that the transition functions, once we have a spinor, are in SUD, or in this case, SUD over 2, in this case, SU3. The transition functions on this bundle, lambda 3, 0, come from the transition functions on T. And if you work it out, because it's SU3 rather than U3 or SOD, the transition functions on lambda 3, 0 will be trivial. Conversely, if even if you have never heard of a spinor, but you know that this bundle is trivial in this sense, then an omega can be defined. Well, then it is still not enough to say that you have a full spinor, but it is part of it. There is a jargon, so this is really what we need, that the bundle be trivial, but people say C1 equals 0. For us, let's take that as a definition. C1 equals 0, C1 of the manifold. C1 of the manifold is 0 if this bundle is trivial, or in other words, if you can find globally a 3-0 form. But of course, from this notation, you see that it comes from another place, and there is we could give it another definition. This is so-called first Chern class. But it is just some computation that detects whether this bundle is trivial or not. So it will be an alternative characterization of what it means for omega to exist or not. So for us, it will be enough to have this characterization in terms of omega. when omega does not exist, there are tricks. You can still basically define something called a form that is bundle valued. There is a generalization or a twisted form, people call it also like that. There is a generalization of this language that also works when C1 is non-zero, but we can just bear in mind that that generalization exists. But when I will talk about complex structures on a space without this property, you can think of it as having to do with the holomorphic vielbein itself without necessarily having a form, a 3-0 form. So again, what can happen is that you can have this 1,0, you have a basis of 1,0 forms, and you can try to define on every open set an omega, which is the wedge of these 3 1,0 forms, the H's, but they will not glue well. They will not globally make sense over the whole space. So really, an omega might not exist. So there are many other characterizations that don't involve omega. I find when omega exists, this is in my opinion, the best characterization. But there are also, I feel obliged to also mention consider the T10. Now these are 10 vectors, not forms. We haven't defined them yet. How do I define them? Well, I can define them as the vectors such that if you take V times all the HI, you get 0. What's the idea? Wait. The idea is that if these will be, when the complex coordinates exist, these are vectors of this type. And if I do the inner product of a vector of this type, yeah, sorry. Here I want to put a bar with one form of this type, I get 0. So this is the idea of this characterization here. Well, now if you consider the Lie bracket on the first lecture of 2 vectors that are in this T1, 0, well, you should get something else which is still in T1, 0. If complex coordinates exist, this is easy to see from the formula of the Lie bracket. And what is non-trivial is that this also goes the other way, that if this condition is true, then you can, it turns out that you can also find the complex coordinates. And why did I say that I feel obliged to say this? Because there is a language in which you this leads to the, if you impose this in real coordinates, you will find something called the Neuhaus tensor. What I'm saying is people sometimes write a projector on this T1,0, and then they impose this condition very explicitly, and they will get a complicated tensor, basically in terms of our J, where we raise one of the indices of J with the metric, and then we put it on here. It looks something like this. So it will become a basically this condition will become a complicated equation in terms of this I. And this is what you often find in books. So, okay, these are many possible characterizations of complex, of manifolds in which there are complex structures. I didn't say it, but manifolds in which complex structures exist are called complex manifolds. Very good. Can you still hear me? I can get a message. Very good. Okay. Because a couple of times I got a message threatening that my internet connection was not good. Now, we have only a few minutes, and I could give you further characterizations of complex manifolds. But perhaps I will skip that for now, because I want to use these few minutes to introduce a special type of complex manifold that will be important in the rest of these lectures, but also for the lecture tomorrow, for the seminar tomorrow by Watari. So I'm skipping a couple things just to be able to say that when also we have this condition, a second condition. So we had a condition on omega so far for complex to call our space a complex manifold. If moreover this is true, we say that our manifold is scalar. It might be a bit a mystery for now why I'm imposing all these differential conditions. Mathematicians have their own reasons for imposing these conditions. I think hopefully, given my discussion in terms of the HI, might be clear why mathematicians might be interested in having transition functions that are holomorphic. It is perhaps a little less clear if you have never seen why you would impose this condition, dj equals 0. If you have only this condition, then you say that M is symplectic. Where does this come from? Well, This comes from the theory of phase spaces in classical mechanics, which can be reformulated in terms of two forms like this. In classical mechanics, you have the Poisson brackets. The Poisson brackets can, of course, very easy to write on the phase space of a particle, but mathematicians have generalized them with a two-object index to, instead of having dp dx minus dx dp. So they have generalized the Poisson brackets with a two-object index that tells us what derivatives to take. And it turns out that that two-object index, so the brackets defined this way, satisfies the Jacobi condition of Poisson brackets if and only if the two-object index, when you lower the indices and you bring it down, becomes the J two form that is closed. So this condition basically comes from the Jacobi condition for Poisson brackets in the study of classical mechanics. This is a mathematical reason to introduce this object. For physics, it will become, as we will see next time, from a study of the spinors in physics, because for now I have introduced these spinors by themselves. I haven't put them in physical theory. What we will see is that we use them in physical theories. Well, we know that you know already that we use spinors in physical theories, but in particular for supersymmetry, this will be the parameters of the transformation, and then the condition that this supersymmetry will should be unbroken will impose some differential conditions on this eta, and that differential condition will translate into differential conditions on omega and eta, because after all they are defined from eta, from the spinor eta. So even though now these conditions might look a little mysterious, they come naturally from physics. Well, I've simplified a bit the discussion. Wait for the rest of the lecture so to see how this comes about. Okay, our discussion actually of complex manifolds. So not all complex manifolds are scalar, but most of the complex manifolds that we encounter both in math and in physics are scalar. I will comment on the difference, but so next time I will discuss a bit more the properties of these two manifolds, and then well, and with this I will conclude. I will comment on the fact on the particular case where in particular we do have that C1 equals 0 on top of scalar. I told you that a complex manifold can also not have this condition. It is convenient when it does. Complex with symplectic is scalar. Complex with symplectic and C1 equals 0 will be an even more special type of scalar manifold called a Calabi-Yau. So with this preview of the next lectures, I think we can conclude for today.